Hello and welcome. My name is Andreas Weber. I am a developer here at Math2Market. Together with Dennis Hoch from the Hochschule Heilbronn, I will give a talk about oil mist filtration, or in more detail, on the simulation of coalescence of droplets inside those oil mist filters.
Also from my side, hello and welcome to the GeoDict User Meeting 2021. As Andreas Weber mentioned, I'm Dennis Hoch from Hochschule Heilbronn, and I'm happy to give this talk today together with Andreas Weber. As you can see on the slide, this is our agenda. First, we start with the motivation for this new GeoDict implementation. Then Andreas Weber will talk about his new method to simulate liquid droplets on a filter structure via a distance map. In the following, I will talk about how we make sure that the GeoDict module delivers useful results. The last thing to go is the summary and outlook. So, there are a lot of coalescence filters on the market, like compressed air filters or oil mist filters. And on the one hand, oleophilic fiber structure is beneficial for catching droplets. On the other hand, oleophobic fibers are beneficial for the drainage process. So the idea is combining both positive properties and resulting in bicomponent fibers. Therefore, we are currently working together with other institutions, as you can see on the slide on the right side, on a public funded SIM project. It's called BicoFil. And the challenge is to improve the efficiency without decreasing the pressure drop of the filter material.
As you have seen, we are working together with many different partners in this project. But the Hochschule Heilbronn is the most important partner for us. They are trying to simulate the coalescence of the oil droplets using the software StarCCM+, while we are trying to develop our own model and do the coalescence using GeoDict. The Hochschule Heilbronn is analyzing and comparing all the simulations that they have done and that we have done, and they are trying to find matching results, and they will give feedback to us how we can develop our model further. And we are trying to develop our model and integrate it into FilterDict simulations at the end. And hopefully at the end we will have a nice simulation which is also much faster than, for example, with StarCCM+. So let's start right off, and I will give you some slides on how we want to simulate the coalescence using GeoDict. Here you can see how we do our simulation of droplets. Basically, we'll just do a classic FilterDict simulation as if we had resolved solid particles, but we will simply change the droplet density according to the fluid material. For example, if we have water droplets, we will change it to 1 kilogram per liter, and we will change the droplet interaction on surfaces to the option caught on first touch. It looks like this here. Our particles move with the flow and will be trapped on the fibers immediately. This next step here is something new. Normally we would just add more and more solid particles to our filter, but now we have to fluidize our particles such that they can coalesce with their neighboring particles. And then we have to reshape the volume based on the contact angles. It looks something like this here. So we are taking the starting positions for our droplets and convert it to a volume field. And then our next step is simply to repeat the steps from before. We will add more particles, we will fluidize them, we will coalesce them with their neighbors, and then we reshape the volume again based on the contact angles. It looks like this here. We have more and more fluid volume, and also the shape of all our droplets is changing all the time. I will now go into more detail on how our coalescence steps work. And the first thing is how to combine touching droplets so that they coalesce into a larger single droplet. And we just do this by taking the volume fraction field of our fluid. So each droplet now here creates some kind of a circle in the volume fraction field. We will threshold this field at 0.5. That means at least 50% of our voxel has to be fluid. And then we will do a component graph on that, which is the second picture here. And this will identify touching sections. We will just sum up all the volume of each section and place a new droplet in the middle of the section. And then now we have coalesced droplets ready to go. The next step is now to find the perfect shape based on the contact angle. And this is done by using a combination of geometric operations while keeping the volume conservation. And we decided to do this because we do not use two-phase flow simulation like StarCCM or surface energy minimization like Surface Evolver, which will give us an extremely fast solution. On the downside, we have a little bit less accurate solution at the end. As you can see here, the analytic solution in red is a little bit different than our solution, but I think it's still quite a good match. Even more details on how to get this geometric operations done is given here. So each droplet center point will be calculated, and from this we will simulate the distance. So this is shown here on top right picture. You will see the center point distance. Also, we will calculate all the distance from the surfaces, from the walls, and we get something like this down here. And also we will do each calculation inside each droplet's own Voronoi section. So we will subdivide our volume into smaller sections where only one droplet will live. We will now combine the wall distance and the center point distance and weight both of them according to our contact angle, and we will get something like this here, the combined distance. As you can see in each section, it totally looks different because we have different contact angles for the left and the right droplet here. We will now threshold this field while trying to conserve the volume of the starting droplet, which will give us the shape shown down here. And again, here the red line is the analytic solution, which will also again show quite a good match.
The next part is how we check the results of the simulation by Andreas Weber. The simulation results from Andreas Weber are the pressure loss over time and load and the deposited oil in the filter material. But for checking the results, we have to start earlier. The first thing we compared was a single droplet on a fiber. To model the shape of a single droplet, I used the volume of fluid method. On the right side, you can see such a volume of fluid simulation of a droplet between two fibers. The volume of fluid, the WOF method, is a free surface modeling technique. The numerical technique is used for locating the fluid-fluid interface of Eulerian phases, which can be the surface of a droplet, for example. The volume of fluid model takes the surface tension, the contact angle with solid boundaries, and the density of the fluids into account. But it is not a standalone flow-solving algorithm. The Navier-Stokes equations describing the motion of the flow have to be solved separately. While the volume fraction is tracked at each cell, All fluids share a single set of momentum equations and one velocity field. Therefore, the pressure loss cannot be determined correct in the volume of fluid simulation. Only the shape and behavior of the phases. But how do I make sure my results are correct? Therefore, I have set up a very simple capillary rise simulation. So I can compare my results to the analytical calculations of the capillary rise in a tube. The diameter of my simulated tube is 2 mm, and the wetting angle of the fluid, in this case water, is 60 degrees. On the bottom is a stagnation inlet, and the top of the tube is a pressure outlet. On the slide, you can see a 2D plane through the simulated 3D tube. As you can see, the results show good agreement with the calculated height. The small differences between the simulation and the theory are because of the semi-empirical equations used in StarCCM+. The semi-empirical equations tend to map the contact angle slightly larger than it is in reality. These differences are smaller than the discretization of the droplet. In the next step, I use the physics of the validation and slide before for simulating a single droplet which hits a small section of a filter. All fibers have a contact angle of 60 degrees, and for this simulation with the filter, the droplet is 30 micrometers wide. The droplet is injected with 0.1 meter per second, just like the air velocity. As you can see on the GIF, the droplet sticks to the fiber that is touched first, because of the wettability of the fiber. On the top right side, you can see the resulting shape of the droplet in the fiber structure, depending on the contact angle between the fibers and the droplet. Because of the small droplet volume in comparison of the pore volume of this filter material, the exact droplet shape has no significant influence of the pressure drop in this specific case. With higher saturations, the influence of the liquid phase and the fiber wettability has more influence of the pressure drop.
Next up, we will show you some results and discussion. Okay, here you can see our results. This was one of the first solutions that we did. You can see a droplet between two fibers, and on the left side this blue droplet is simulated using StarCCM, while on the right side here this yellow droplet is the result from the GeoDict model. And in the middle we have the combination of both, where the overlap is shown in magenta. As you can see, 80% of the voxels of all the fluid voxels is overlap, so we have quite a good match of both these droplets here. We also did different kinds of configurations of fibers, so in which kind of angle they will meet, and also which contact angle is on the upper and the lower fiber. And overall we give something like this here, so approximately 80% overlap of both droplets was possible. Here you can see some results of a filter lifetime simulation using our new model. So particles and droplets are added each batch, and as you can see, we have increased size of droplets forming in our filter. And here you can see the corresponding graph of deposited dust, which is now more or less deposited fluid, and the pressure drop. And according to what we have seen in the last slide, the pressure drop will increase because the fluid will block more and more paths through our filter. And normally at the end you would see some kind of plateau phase where the filter is completely saturated with fluid. At this time we did not get a nice plateau phase so far, but I hope that for the next presentation I can show you some better results. We are slowly coming to an end, so now we will give a summary and an outlook. So as a summary, I will show you this video, which shows approximately the state at which we are at this moment. So you can see our model is working quite well, and also this filter cutout here is often rather smaller size, but yeah, could be usable as some kind of simulation result for your laboratory. Yeah, and to give you some outlook for this slide here, where you can see which things we are trying to do next. So the drainage simulation in the volume of fluid method, so with Stasis and Plus is the next step, and for sure then it comes to GeoDict as well. This means what will happen if the oil filter is saturated, how does the oil leave this filter again? Because in the real world filter this for sure happens. For example, the oil is just running down due to gravity, and this is one step that is still missing in our simulations. And yeah, as you can see, we will try to take the same path as before. We will start with some single fiber, simple geometries, and then go up to a mini filter. Yeah, and then the next step after all this has been done is the final validation, more or less, which means comparing the pressure loss between different methods, which has not been tackled so far, and is hopefully leading us to a nice filter model at the end. And also, having the validation for sure is a really important step, especially for all our customers, because otherwise we could not sell our nice new models here. Yeah, that's it for today's talk. Thank you very much, and we are happy to answer all your questions.